Anybody have any questions before I get started? Thanks, Darius. I was wondering if I'd get an email back from you. I haven't been able to check my email at all since about mid-afternoon yesterday. So it's probably just that I didn't see it. I've been dealing with some things going on this side of the world. uh, but anyways, yeah, I'll go ahead and get that done for you, and we'll work on getting you caught back up, bud. All right. So last time we met, we were in chapter 9. We had worked out some useful equations for collisions in one dimension that were happened to be elastic, and we got a nice little equation: VA minus VB is equal to the negative of parentheses. VA prime minus VB prime, close parentheses. And that could be used in conjunction with the conservation of momentum equation, or it can be used in conjunction with the conservation of kinetic energy equation. Generally, we just use it with the conservation of momentum equation, and that allows us to figure out all the information we need because you normally just don't just have no knowledge of two quantities, and two equations is really all you need. So right now we're going to start on example 9.9, which is us going into another example, but this one's a more quote unquote physically realistic one because it's a proton bombarding a stationary alpha particle. And alpha particle, remember, is the nucleus of a helium atom. So it's basically two protons and two neutrons bound together by the strong nuclear force. So let's go ahead and get started with example 9.9. And I'm going to start by sharing my screen with you guys. Okay, this should come on any second now. So this is example 9.9. I'm going to read it to you like I've been doing. So again, this is another time where it's best if you actually have your textbook, your ebook open so that you can look back and forth between the actual questions, but I will be reading them in their entirety. So this is example 9.9, a nuclear collision. It says a proton P of mass 1.01 unified atomic mass units traveling with a speed of 3. Excuse me, of 3.60 times 10 to the fourth meters per second has an elastic head-on collision with a helium nucleus. M sub helium is equal to 4.00 atomic mass units, unified atomic mass units, initially at rest. What are the velocities of the proton and the helium nucleus after the collision? We can actually do a conversion factor, use a conversion factor to get us from unified atomic mass units to kilograms, but we really don't need it because it'll turn out that the conversion would cancel out anyway. But the conversion, just in case you're wondering, is one unified atomic mass unit is 1.6605 times 10 to the negative 27th kilograms. So let's go ahead and get started with this problem. Again, what we've been given is we have MA is the initially moving particle, and that has a mass of 1.01 unified atomic mass units. Mass B is the mass of the alpha particle, which is 4.00 unified atomic mass units, and VA is equal to 3.60. Actually, I wrote that kind of small, so it makes it kind of hard to see. So 3.60 times 10 to the fourth meters per second, and then of course VB is equal to 0, but what we want to know is VA prime and VB prime, which are, of course, the final velocities of the proton, which is the 1.01 atomic mass unit, and VB prime is the final mass, or excuse me, the final velocity of the alpha particle, which is the 4.00. So we're going to work it as follows. What I'm going to make use of is the result that I derived for you last time, and that derivation is something worthwhile to memorize. But to be honest with you, you really only need the result. The big thing is the memorization of the process in which you solve for it is very helpful in that it gets you a little bit more comfortable with solving systems of equations algebraically. So that equation that we found was VA minus VB is equal to negative parentheses VA prime minus VB prime. And then, of course, we also have the conservation of conservation of linear momentum equation, and that is MAVA. We're talking one dimension here, so MAVA. And since this one has the target particle, the MB, moving at zero initial velocity, I'll just write plus zero is equal to MA VA prime plus MB VB prime. So that's what we're going to try to make use of and see if we can solve this problem for VB prime and VA prime. So if we go ahead and plug in our values, for instance, in terms of VB, VA prime, and VB prime, we can take this first equation, which I'm going to label 1, and the second equation. I'm going to take the first equation first, 1. This is going to be, in fact, the VA is the velocity of the proton. I'm going to go ahead and keep it as a symbol. So I'll just say VA minus 0 is equal to, now I'll distribute the negative, and I'm going to say this is VB prime minus VA prime. So this equation we can call 1 because it is the same equation. All I've done is just submitted the specific values, and even then I just still using the symbol, but I did submit the 0 in there. Now, in addition to that, we can use this to solve for one of the velocities. So what I'll do is solve for the velocity of the proton, for instance, after the collision, and that one is VA prime, which if I pull to the left-hand side, it'll become positive. Then I'll get VB prime, and then I pull the VA over to the right-hand side, that'll be negative. So it'll be VB prime minus VA. So that should actually uh, work. Now, if I take and plug this equation, which I'll call 1 prime, if I take that equation and plug it into 2, I can go ahead and solve. So let's do that. Plug 1 prime into 2. When I do that, what we're going to see is MAVA is equal to MA times, now I'm going to substitute VA prime, which is from equation 1 prime, is VB prime minus VA. And then I have the second term, which is MB VB prime. Now I can multiply through, get rid of the parentheses, in other words, and that'll give me MAVA is equal to MAVB prime minus MAVA plus MBVB prime. So you see that you basically only have one unknown now, that's VB prime, and I'm going to go ahead and add MAVA to both sides. That's going to give me 2 MAVA, and I'm going to get factor out the common VB prime, and that's going to be MA plus MB parentheses VB prime, like that. And now that tells me that VB prime is in fact equal to 2MA over MA plus MB, which you'll notice looks just like that equation last time that I told you was like the tension equation from the Atwood machine. So we can go ahead and plug in our numbers. This is 2 times 1.01 U over 1.01 u plus 4.00 u. And then, of course, VA is 3.60 times 10 to the fourth meters per second. Now, that is strictly speaking 1/10,000th of the speed of light, so that's not really an issue where we'd have to bring into account relativity. So let's go ahead and do the calculation and know that we're relatively safe not using relativistic equations because 3.0 times 10 to the eighth is the speed of light, and this is 3.60 times 10 to the fourth, which is almost 10,000 times smaller. So I'm going to take 2 times 1.01, and then I'm going to divide that by 1.01 plus 4.00. That's going to give me 0.4032, and that's a massless or a unitless quantity. Notice the u's you can sort of picture as canceling out with one another, and then all of this, of course, is times the 3.60 times 10 to the fourth. So, and I'm not taking time to write out the 3.60 times 10 to the fourth. I just put dot, dot, dot. And this gives me 1.45. And carrying one extra sig fig would be 1.451 times 10 to the fourth meters per second is equal to VB prime, which is V alpha particle prime. So that's the final velocity of the alpha particle, which is way more massive than the proton, but it obviously took off pretty fast, a little less than half the velocity that the proton had. Now we got to calculate what the velocity of the proton was, and the velocity of the proton, luckily, we already solved for in terms of equation 1 prime. So 1 prime, oops, sorry, still in red. So from 1 prime, we get velocity A prime, which is the proton after the collision. That is equal to the velocity of B prime minus the velocity of A. And of course, that is VB prime 1.451 times 10 to the fourth meters per second minus VA, which is 3.60 times 10 to the fourth meters per second. So when I subtract this, I'm obviously going to get a negative number. And this gives me 2.149, negative 2.149. I'm carrying one extra or one extra digit, of course. So 2.149 times 10 to the fourth again meters per second is equal to V proton. So the proton, when it actually hits the alpha particle, will actually recoil. It's going to bounce backwards. And it bounced backwards with about 2/3 of the speed that it had before the collision. So, anybody have any questions on that? Oop, got another person tried to come in. All right. All right. I'm not showing the chat right now, so I want to make sure I put that up. All right. Now the chat window is open again. So if anybody needs to make any questions, you can chat on there, or you can also, as always, I hope you guys would actually speak out if you have any questions. So please do that. I mean, I'm feeling a lot lately like class is going really smooth, but I'm afraid it's really going awfully because I'm just talking and I feel like I'm sort of steamrolling you guys, and I don't want to do that. I want you to ask me questions if I'm confusing you or anything like that. So please stop me if I'm going too fast or if you don't understand something I do. And don't feel bad. I mean, if you have a question, there's a high probability that two or three others in the class have the exact same question. So, All right, now that we've completed that, we're going on to the next section, which is talking about inelastic collisions. So we've already talked about collisions in which kinetic energy is conserved, and those collisions are called elastic collisions. Uh, Collisions in which kinetic energy is not conserved are called inelastic collisions. But then there's also a special type, which I've already hinted at and told you about before, and that's when two objects collide and stick together so that now they act as one big mass whose mass is generally the sum of the two original masses, and they have one common velocity. So that's what we call a completely inelastic collision, and that's what we're talking about now. And one of the first examples we're going to work on that is something called the ballistic pendulum, and this is example 910. So let's start example 910. So it says a ballistic pendulum is a device used to measure the speed of a projectile, such as a bullet. The projectile of mass m is fired into a large block of wood or other material of mass big M. So they're using lowercase m for the projectile and uppercase M for the big hanging block of mass or block of wood. Uh, which is suspended like a pendulum. Usually m is somewhat greater than lowercase m. As a result of the collision, the pendulum and the projectiles uh, together swing up to a maximum height h. Determine the relationship between the initial horizontal speed of the projectile v and the maximum height h. So that's what we're trying to figure out. What we have is a mass m that we know, a mass big M that we can assume we know, and we're also going to assume we know a height h. And what we want to find is the initial velocity v is equal to question mark. Now, just so you'll get an idea, in case some of you don't actually have your book open, here's a rough picture of the events that are occurring. So you can imagine, for instance, there's a string or two strings, and they're tied to a rather large mass, big M. And what we have is a mass, little m, moving with a velocity, little v. And sometime later, the mass, little m, is going to embed itself into the mass, big M. And then the mass, big M, is going to swing to some height like this. And this is the height h that we're talking about. Okay, so that's basically 3 points in time, all showing the same drawing. The first drawing being basically just the blue, the second drawing being just the dotted red, but the third drawing being the actual solid red. Sorry, I wanted to make that a little more obvious. So there's the three times: solid blue, dashed red with solid blue, and then all solid red. So what we're going to do first is conserve momentum. So solution, if we treat the system as if it's just the bullet and the hanging mass M, then the net external force on it really is zero. There is obviously a gravitational force pulling down on the little mass of the projectile, but that's not going to be significant compared to any of the other forces. And it's then going to embed itself in the mass big M, and that is a huge force. But that's an internal force. That's a force of one part of the system acting on another part of the system. So you don't have to count that in the summation of forces equals dp dt. Therefore, the summation of forces is equal to zero, dp dt is equal to zero, therefore P is a constant, and that's the definition of conservation of momentum. So in this case, we're going to have P initial, and I'm using uppercase because this is obviously a two-part system. It is one-dimensional, so I'm not going to waste my time on vectors, but and vector symbols. But the initial momentum is just m times v, and then the final momentum. Now this is just for immediately after the block, the bullet embeds itself in the block. We're not talking about after it starts to take off, because once it embeds in the big mass, the momentum is going to be transferred to the big mass, and it's going to leave with a new velocity, which we'll call v2 or something like that. But that's the point where we stop looking at it from a conservation of momentum standpoint. At that point, we start looking at it from a conservation of energy standpoint. So the final momentum is going to be m plus m times v2. And in this picture, v2 would be, oops, I should draw this in red to keep it consistent with my color diagram. Okay, that's the velocity that the block mass system is going to take off at. Now I can say P initial is equal to P final, and from that I get mv is equal to m plus m times v2. But I need to figure out in terms of v2 how I can relate that to h, because ultimately what we want is v in terms of m, big M, and h. So now I'm going to use conservation of energy, and it's conservation of mechanical energy. Now, I took the time to tell you it's conservation of mechanical energy, so I wouldn't have to write mechanical energy, and then I wrote it anyways. Anyways, what we normally know of as our conservation of mechanical energy is U initial plus K initial plus or excuse me. Yeah, I could say work in. I think that's what I used to call it. So plus work in is equal to U final plus K final plus work out plus E loss. So that was the version of conservation of energy I told you guys to use. We're going to say E loss is zero. We're going to say work out is zero. We're going to say work in is zero. And we're going to call the zero of potential energy basically the initial position. So potential energy is initially zero, which I can write like that. And then at the peak of its height, the kinetic energy is going to become zero, so I put a zero there as well. So this gives me just 1/2 m v squared is equal to m plus m times g times h. And, oh, excuse me, and this velocity, by the way, is v2. And actually, I messed up a lot of stuff there. Sorry about that. Remember, we're starting to study this in the dashed red, or in the red that's not solid lines. So the whole mass system is moving at velocity v2. I left off the v2 and I left off the other mass. So that's the mistake I made. Luckily, I caught it beforehand. But anyways, 1/2 mass of the system, v2 squared, is equal to mass of the system, and we're very close to the Earth's surface is what we're assuming, so the potential energy is just mgh, which in this case is going to be parenthesis m plus big M close parenthesis gh, and with that we can solve for v2. So with this we can say that v2 is clearly equal to the positive square root. What we can see right now is the m plus m is common to both sides, so we could divide both sides by m plus m, and that would just give us 1/2 v2 squared equals gh. So v2 squared would be equal to 2gh, and v2 is therefore the square root of 2gh. So now we've got V2, and I can plug V2 into the result from conservation of momentum, and we get the following. So I'm going to say plug V2 into conservation of momentum. So in doing that, we're now going to have mv is equal to m plus m times v2, but now we have v2 is equal to the square root of 2gh. So I put that there, and now I'm in the position where I can ultimately just solve for v. And when I do, that would give me essentially what we'd call the muzzle velocity of the gun or whatever object shot the projectile. And the result is m plus m over little m times the square root of 2gh. And that's the ballistic pendulum result. Anybody have any questions on that? Okay, looks like we do not. Now, I will tell you, and I meant to tell you this just before class started, but I need to tell you as soon as it comes to me. I just double checked just before class started. I do have right now two online tests are open. The online test that goes up through chapter 8 is due by July 14th, and then the online test that goes up through chapter 10 is due by July 21st. Obviously, July 14th is the one coming up pretty soon. I think I opened that a long time ago, but I just wanted to let you know it is up there and you are expected to get that done by the 14th. I'm having a problem where about two or three students are missing online tests when they're missing the deadlines for online tests. So I'm stating it again in class to remind you guys, don't miss your online tests. They're part of the whole pedagogy of my course where I've learned that if I give my students the practice test and an online test prior to taking a face-to-face test, my class average for the face-to-face test is a lot harder. And you folks have actually shown this to be true as well. My class averages on the face-to-face tests are usually in the upper 60s to lower 70s, whereas quite often before I implemented this system, I would get in the upper 40s and to low 50s. So y'all are doing a much better job, and obviously it's more work, but it's really basically what we're doing is trying to get you in the idea of doing a lot more homework than the bare minimum. And by doing practice tests and online tests, that's sort of the equivalent of what we used to tell our students is like, do all the odd problems at the end of the chapter. Because the odd ones had answers, you could check your work, and that really is sort of the standard. And in fact, in some cases, you need to do not only all the odd ones, you might need to do some of the even ones too, just to make sure you fully understand the material. So everybody keep that in mind. Two online tests coming up. Also next week, if I remember correctly, I've changed the setting in the syllabus to let everybody know, but our actually the syllabus is always been correct on the face-to-face test. So we do have a face-to-face test coming up. So make sure you're ready for that. I will remember for those of you who are in my NO2B class, I will remember this time to send it to Mr. John or Dr. Johnson. So anybody have any questions before I move on to the next example? All right. So there's another example. It's example 911, and this is hinting at another result that's kind of important. But it's basically those same train cars, and they're asking a very different question. So it says railroad cars again. It says for the completely inelastic collision of two railroad cars that we considered in example 9.3, calculate how much initial kinetic energy is transformed to thermal energy or other forms of energy. In other words, what they're trying to figure out is exactly how much kinetic energy was lost. And that's actually a very typical calculation for inelastic collisions. And there's a very typical symbolic result that you can get. And that's what we're doing. So I want to remind you the train cars had masses of 10,000 kilograms because they were identical. And if I remember correctly, one train car was moving at 8 meters per second and the other train car was sitting still. I'm going to click on this real quick to double check. I clicked on the example just to make sure. Yeah, it was 8.0 meters per second. So what we have here is M1 equal or MA equals MB is equal to 10,000 kilograms and VA is equal to 8.0 meters per second and VB is equal to 0. And then what we want to know is VA prime, which equals VB prime, which equals just plain V prime. That is sort of the question mark, but it's only the question mark in the sense that we need to calculate that. Or we could, of course, just take the figure that we got from when we did that example. But the main thing is we either have to solve for that V prime again and then use it to calculate the change in kinetic energy or the loss in kinetic energy. So I'll say K loss is equal to K initial minus K final. That's really what we want to find out, and that's equal to question mark. So I put the question mark after equals for the V prime, but that's not really the crux of the question. The, and in fact, the V prime that I'm saying we're going to have to solve for turned out to be 4.0 meters per second. So we could calculate it that way. But what I'm going to do is go ahead and work it generally and just in terms of the M's and everything so that you can see the actual result. So what we have here is a train car moving with a velocity VA having a mass, which we're just going to call M, and let's call it MA because I want to work it in terms in general anyways. And this is a train car with a mass MB. Of course, in this particular example, the train car MA and MB are equal. But then after the collision, they are stuck together and moving with a velocity v prime. Okay, so conservation of momentum gives us MAVA is equal to MA plus MB times V prime. Therefore, V prime is equal to MA over MA plus MB. And all of that, of course, is times VA. So that's the final velocity for any generic system where the target particle is sitting still and it could have any mass. So I'm working it most generally, and then we can put out exactly the right results for the train car just by plugging in the values of MA, MB, and VA. Obviously, you can see that VB or V prime in this case is going to be 4 because you get 10,000 over 20,000. That's obviously 1/2 times VA, which is 8 meters per second, and half of 8 meters per second is 4 meters per second. So now I want to say K loss is equal to 1/2 MA VA squared minus 1/2 MA plus MB V prime squared. So that's the actual change. Now I'm going to plug in what I know as V prime. And oops, really hate this GoodNotes program. I'm not impressed with it. turning into an eraser at the drop of a hat. I can factor out the 1/2, but the main thing I need to do is go ahead and plug in the v prime. So this is going to be 1/2 ma va squared minus 1/2 ma plus mb. Now times v prime, which would be ma over ma plus mb, va, and this whole quantity right here has to be squared. Now, I really overestimated my ability to fit this in space. I'm going to copy it to the next page using my little lasso. So here's my little lasso. I'm going to say copy, turn over to the next page, and I'm going to say paste. And that looks pretty good. And of course, now I'm going to go ahead and do some nasty algebra. This is a way bigger, fancier problem than the one we're asked. Trust me, the one we asked was a lot simpler. But now I'm going to go ahead and do the multiplication, all that stuff, get a common denominator. This is ma va squared minus 1/2 ma plus mb, and then the square of all this gives me ma squared va squared over ma plus mb, again squared. So you can see right now that the MA plus MB is going to cancel out with one of the MA plus MBs in the denominator. Therefore, our denominator is going to be MA plus MB. So I'm going to multiply the first term by MA plus MB over MA plus MB. In doing so, let's go ahead and just pull the 1/2, which is common to both of them, completely out in front. So in doing this, this is going to become MA times MA plus MB over MA plus MB. And then, of course, this is all times VA squared minus the second term. And the second term is going to be MA squared VA squared over MA plus MB. And you see that we do have, in fact, a common denominator. Now I'm going to distribute, leaving the 1/2 out in front still, and this becomes ma squared plus MB plus, excuse me, all of that has to be times VA squared. But notice the other one has a VA squared, so I can actually pull that out and to the side as well, and I think I will do that. Minus MA squared VA squared. And then, of course, all of that is over MA plus MB. Now, I can write this as 1/2 VA squared. And now I see MA squared minus MA squared because I'm factoring out the VA squared. So that VA squared that appears in these terms is no longer there, but those two definitely cancel out. But now I have all that's left on top is MA, MB over MA plus MB. And that is our actual result. So what we see is K loss is equal to 1/2 MA MB over MA plus MB times VA squared. And quite often we normally write it as K loss over K initial. So it's the fractional loss. And of course, you see what happens then. Since the initial kinetic energy was just 1/2 ma squared, you can see the 1/2 is going to cancel out, the ma is going to cancel out, and the va squared is going to cancel out. And this is the simplest, prettiest result you can get. We just get mb over ma plus mb. So these are really the major result. That one that I just boxed off is what the book asked for. It's actually still bigger and better than what the book asked for, but it's closer to what the book asked for. So now I can go ahead and plug specifically in what the book asked for, and I'll say K loss is equal to 1/2 10,000 kilograms times 10,000 kilograms over 10,000 kilograms plus 10,000 kilograms times the initial velocity squared, which would be 8.0 meters per second quantity squared. So now what I can do is say zero point 0.5 times 10,000 times 10,000 times 8 squared. And now I'm going to divide that by 20,000. And this gives me 160,000. And you can see that the units turn out to be kilograms meters squared per second squared, and a kilogram meter per second squared is a newton, and a kilogram meter squared per second squared has to be a joule. But of course, we only had two sig figs, so these last four digits are in fact not significant. So we'd say the result is K loss. Oops. The result is K loss is 1.6 times 10 to the 5 joules. So that's more specifically what the book asked for. But notice the neat, useful formula that we found. Basically, the loss in kinetic energy divided by the initial kinetic energy, and therefore it's called the fractional loss in kinetic energy, is mb over ma plus mb. Anybody have any questions on that one? And if you remember the original kinetic energy, just to give you an idea, K initial was 1/2 times 10,000 kilograms times 8.0 meters per second squared, which is equal to zero point 0.5 times 10,000 times 8 squared, gives me 3.2 times 10 to the fifth joules. So as your book advertised, in fact, it lost half of its kinetic energy. No questions? All right, now I'm getting ready to get into the part where I warned you. This is where we're going to talk about two-dimensional collisions. And in so doing, I'm going to show you a very specific mathematical technique that you just need to learn. Okay. It's just super helpful. And if you learn this one, you can always use it. Whereas if you don't learn it, you're going to try to figure out how to solve a system of equations over and over again. And I'll tell you that based on my experiences, I didn't realize the importance of this particular method. So I was just doing something every time, and it was really, really hard. I really had a bummer reaching the conclusion that, holy crap, I'm just not that good at solving systems of equations. And it turned out that's because this particular idea is really the best way of doing it. So let's start off with the scenario, and it's going to seem like it's not general enough, but it really is. Let me show you, and then we'll explain that. So what I'm going to imagine is we have a particle, and actually I should really move that down a little lower. Let's see if I can. It looks like I'm going to just delete that, and I'm going to draw it a little lower myself. Okay, so there's the particle. This particle has a mass ma. Oops, there I am on my automatic drawing. This particle has a mass ma and has a perfectly horizontal velocity va. Okay, but it is specifically horizontal, and that is part of the idea where I'm telling you that this seems like it might be not be a perfectly general problem, but in fact it is. And again, I'm going to explain that in a second. Now I have a target particle, and again, this is another part that makes it seem like a very special problem as opposed to a general problem, but again, it's not. So I have a target particle, and this target particle, uh, I'm trying to draw it. There you go. This target particle has a mass mb, but it's sitting perfectly still. Now, here's where I'm going to embed this in a coordinate system. And again, it's going to seem like I've given away a lot of potential freedom by assuming the initial particle, the ma, is moving in the positive x direction. And by assuming that the particle mb is sitting perfectly still, but I will tell you that it's not, because you can always switch to a coordinate system in which the x-axis is aligned with the initial particle's velocity, and in which the initial particles, or excuse me, the target particle, the one we're calling MB, has a velocity of zero. So you might actually have to switch to a different coordinate system, a coordinate system that's parallel, for instance, to your accelerator. The x-axis would be parallel to the accelerator beam, and we would also imagine the lab to be moving at whatever velocity MB would have. And in so doing, the velocity of MA that it has in the lab is very different from the velocity that it's going to have in this new frame that's moving along with the target particle. But the result is the target particle has zero velocity, and therefore this whole setup is in fact completely general. Okay, it just takes one coordinate transformation to see otherwise. Okay, or to see that it is. So we're going to say one of these particles, possibly A, is going to take off at an angle theta A, and this is something that's after the collision, so they put a prime on it. Uh, Whoa, that was not good. And the velocity of this particle at the end, of course, well, that was not helpful. The velocity of this target particle is VA prime. You could also say the momentum is PA prime. That would be acceptable. And we're also going to say that acting at a potentially different angle is the angle theta B prime. That's a negative angle. And in this case, we're imagining that the particle is moving off with a velocity VB prime. And this, of course, is MB. And this guy up here is still MA. So that's the whole collision. What we're seeing to the left of the coordinate is, and right on the coordinate origin, is the initial setup, and then what we're seeing to the right of the coordinate origin is the trajectory that MA will follow after the collision, and the trajectory that MB will follow after the collision. And it probably would help for me to just point out that that's what MB is. Now, from this, we can get the conservation of momentum equation and the conservation of kinetic energy equation. But right now, we're just assuming that it's going to be a collision that only conserves momentum. Okay, so the net external force acting on the system is zero, but we don't necessarily know that it is an elastic collision. So when I do this, I can write conservation of momentum. I've got to break it down into vectors. It'll be a momentum in the x direction and a momentum in the y direction. So first off, I'll say conservation of momentum. Anybody recall what condition must be true for momentum to be conserved? No one? Remember, that's something I warned you that it's something you should be able to answer at the drop of a hat. So go find out. And then the other thing, can anybody tell me under what conditions is kinetic energy conserved? That's another question I told you guys should be able to know at the drop of a hat. In addition to things like state Newton's first law of motion, state Newton's second law of motion, state Newton's third law of motion, state Kepler's first law of motion, state Kepler's second law of planetary motion, state Kepler's third law of planetary motion. All of those are things that you should be able to just regurgitate at this point in the course and any point later in at least the semester, if not the rest of your life. So keep that in mind. First off, I'm going to take the momentum in the x direction. So I'll put a little x here. And what we have is all the momentum initially is in the x direction. So I have MA VA. But after the collision, then the x component has to be found using trigonometry, and I think you can see that the setting the x component after the collision equal to the x component before the collision gives me MA VA prime cosine theta A prime plus MB VB prime cosine theta B prime. So this is going to be what I call equation one. Now I've got to write another equation for the y coordinate or the y direction. And you see, it, since I told you in the x direction, all the momentum is in the x direction before the collision. Therefore, that means the momentum before the collision in the y direction is zero. So this one's going to become zero is equal to MA VA prime sine theta A prime plus MB VB prime sine theta B prime. That's going to be equation two. Now, this is really all you need if you only have two unknowns and you can readily apply it. So I'm going to show you an example, specifically example 912, and we're going to use these results so far. Anybody have any questions before I go on? All right, so it says example 912. Example 912, billiard ball collisions in 2D. A billiard ball A moving with a speed VA equals 3 meters per second in the positive X direction strikes an equal mass ball B initially at rest. The two balls are observed to move off at 45 degrees to the x-axis. Ball A above the x-axis and ball B below the x-axis. That is theta A prime is equal to 45 degrees and theta B prime is equal to negative 45 degrees. Remember from trigonometry that when we measure counterclockwise from the positive x-axis, that is a positive angle. And if we measure clockwise from the positive x-axis, that's a negative angle. So that's why they're saying what they're saying. And what they're asking for is what are the two speeds of the or excuse me, what are the speeds of the two balls after the collision? So now I'm going to write down the information we're given. What we know is MA is equal to MB, and because they're equal, I'm just going to call that M, and they didn't give us the mass, But as you might suspect from looking at these equations, if all the masses were equal, we could divide equation 1 by m and all the masses would disappear. And similarly, you could divide equation 2 by m and all the masses would disappear. What we are given as well is VA is equal to 3.0 meters per second. And we're also given theta A prime is equal to 45 degrees and theta B prime. Whoa, it just all of a sudden the stupid note program just jumped into auto correcting my drawings is equal to negative 45 degrees like that. And of course, what we want to know is VA prime equals question mark and VB prime equals question mark. So from equation 1, we're going to have, I'm going to go ahead and divide through by the masses. And what we have is VA is equal to VA prime cosine 45 degrees plus VB prime cosine 45 degrees. And now I can also plug in to equation 2. And this one's going to give us 0 is equal to VA prime sine 45 degrees plus VB prime sine negative 45 degrees. So from this, you might be able to take equation 2 and get another response. Oh, it just made it into an automatic auto draw. So 2 is going to become VA sine 45 is equal to, and this will be a negative here, is equal to VB prime, oops, left off the prime here, sine of negative 45 degrees. But you probably recall that the sine of negative theta is equal to the negative sine of theta. So we get negative VA prime sine 45 is equal to negative VB prime sine 45. And from that, we now see that VA prime, they're really getting mad at this stupid program. We get VA prime is equal to VB prime, which we might as well just call VB or V prime. Now, there's a little danger in that because obviously they're in different directions, but their magnitudes are equal. So that's something that's kind of helpful. Now we can plug this in, and I'll call this equation 3. So plug 3 into 1. So if I plug 3 into 1, what I can get is VA is equal to V prime cosine 45 plus V prime cosine 45. Notice I've used VA prime is equal to V prime, and I've used VB prime is equal to V prime. So this becomes 2V prime cosine 45. So we can see that V prime is in fact equal to VA over 2 cosine 45 degrees. So I can go ahead and plug the numbers in. We know that VA was actually 3.0 meters per second. And then we're going to divide that by 2 times the cosine of 45 degrees. And that becomes 3 divided by parentheses 2 times cosine 45, close parentheses, gives me 2.121 meters per second. Of course, that's only 2 sig figs of it is good. So the answer is 2.1 meters per second. And that's VA prime, which equals VB prime. Anybody have any questions on that one? So notice how we were able to just use those equations. This is not the technique, by the way, yet that I was telling you is so important, but it is another easy step. In this case, we only had two unknowns, and they gave us a really beautiful thing that the two went off at a 90-degree angle. You can actually see that that's a result consistent with conservation of kinetic energy as well, because if you look at VA squared is got to equal VB prime squared plus VA prime squared. That would be consistent with theta A prime being positive 45 and theta B prime being negative 45. And that's exactly a right triangle. So from that, you get basically the Pythagorean theorem. If you look at the Pythagorean theorem and you consider it as conservation of kinetic energy, you'd see, I'm going to write this in red here, 1/2 MA VA squared is equal to 1/2 MA VA prime squared plus 1/2 MB VB prime squared. But if you take all the masses are equal, then you can divide through by MA, which is equal to MB, and you can also divide through by 2, and lo and behold, you get VA squared is equal to VA prime squared plus VB prime squared. Now, this is a special case where VA prime equals VB prime, but the fact that they were at a 90-degree angle to each other tells you that this is already true. So that Pythagorean theorem basically just shows you, since the two final velocities differed by 90 degrees, then the two final velocities are legs of a right triangle, and the hypotenuse would be the initial velocity. So what I'm saying is this conserves kinetic energy, even though they didn't tell us to. Any questions? All right, now that we have these two equations, and I'm going to copy them on the next page, so I'm going to use my little uh, lasso. I'm going to copy those to the next page. Copy. And we're going to finish up by including conservation of kinetic energy. So this is the results we have thus far. Now I'm going to say conservation. Whoa, still on my lasso. Conservation of kinetic energy. So for conservation of kinetic energy, what we're going to have, just referring to that same diagram, we're going to have 1/2 MA VA squared is equal to 1/2 MB, or excuse me, let's start with A again. MA VA prime squared plus 1/2 MB VB prime squared. So this will be equation 3. Now, how do we go about combining these in a useful way? Well, the best way is to show you via example. So we're going to use these equations in example 913 and see how that plays out. So let's say example 913. And here it is, proton-proton collision. A proton traveling with speed 8.2 times 10 to the fifth meters per second collides elastically with a stationary proton and a hydrogen target, as in figure 918. One of the protons is observed to be scattered at a 60-degree angle. At what angle will the second proton be observed, and what will be the velocities of the two protons after the collision? So what they've given us here is that MA is equal to MB is equal to the mass of the proton. Okay. We also have that VA is equal to 8.2 times 10 to the fifth meters per second. And what we're told is that one proton scatters at a positive 60-degree angle, and we're not sure what the other one does. Now, I just showed you something about when kinetic energy is conserved when the masses are equal, and I suspect you might be able to guess exactly what the other angle is, but we're going to work this out so that we'll actually know exactly what the angle is. Anybody have a guess as to what the other angle might be? So I would suspect the other angle should be negative 30. So what I'm going to do is just say theta A prime R theta B prime is equal to positive 60 degrees. And I'm going to assume 60 is two sig figs. But here's how we're going to go about solving this. So what I'm going to do first is divide equations 1, 2, and 3 by MA equals MB equals M. And I'm also going to divide equation 3 by 1/2. And that will get rid of basically all that other stuff that we had. So when I do that, what's going to happen to equation 1 is the following. We're going to have VA is equal to VA prime cosine theta A prime plus VB prime cosine theta B prime. Equation 2 is going to be 0 is equal to VA prime sine theta A prime plus VB prime sine theta B prime. And what's going to happen to equation 3 is even nicer. So equation 3 is going to be just that VA squared is equal to VA prime squared plus VB prime squared. So those are our new equations. We might even call them 1 prime, 2 prime, and 3 prime, and that would certainly be acceptable. So what we're going to do now is the trick that I want you guys to understand and learn and memorize and commit to memory so that you can use it over and over again. What we're going to do is take equation 1 and get all the A related stuff on the left and all the B related stuff on the right. So from 1 prime, we're going to say VA minus VA prime cosine theta A prime is equal to VB prime cosine theta B prime. And now I'm going to square both sides. Now this seems awful, but you're going to see some really wonderful things come from squaring this. I would try to write it on the right hand side on that same line, but I don't think it's going to fit, and I think it's important that you see exactly what I have. So I'm going to do it on the line below. Of course, when you square a binomial, you get the first term squared and then 2 times the product of the two terms. So notice one's positive and one's negative, so the product is going to be negative. And then you have 2 VA prime cosine theta A prime. And then finally, you have the square of the third term, or of the last term, excuse me. And of course, the square of a negative is a positive, so this one becomes VA prime squared cosine squared theta A prime. Now, squaring the right-hand side is easy peasy because it's a single term. That just becomes, whoa, there we go again. That time it just turned to the lasso. That is so weird. Anyways, VB prime squared cosine squared theta B prime. So this is a new expression we got, and that's super, super helpful, believe it or not. Now I'm going to do the same thing with equation 2 prime. I'm going to pull the VA prime on the left-hand side, which is going to become negative, and the VB prime term will be on the right-hand side, but then I'm going to square them, so that'll get rid of all the negatives. So when I square the VA prime term, which is on the left, I'm going to get really getting frustrated with this stupid program. This is going to become VA prime squared. This is supposed to be sine squared. VA prime squared sine squared theta A prime equals VB prime squared sine squared theta B prime. So the beauty of this is hopefully you're seeing it now. Anybody see anything that jumps out? Feel free to tell me what you're thinking. What you might notice is if we add these two equations, then the VA prime squared term is going to become VA prime squared parenthesis sine squared plus cosine squared close parenthesis, and sine squared plus cosine squared is 1. So we've basically gotten rid of the cosine dependence in the last term on the equation 1 prime and the sine squared on the first term on the 3 prime or 2 prime equation. So similarly, when we add the right-hand side, we're going to get VB prime squared, uh, parenthesis cosine squared plus sine squared again. So when I add these two equations, I can get this really nice expression. So let's say adding, this is going to give me VA squared minus 2 VA prime cosine theta A prime plus VA prime squared. Notice I don't have any sines or cosines squared anymore because the sine squared plus cosine squared gave me 1. And then on this side, it's VB prime squared. And again, notice I don't have any sine squareds or cosine squared because the sine squared plus cosine squared is equal to 1. So this little expression is super, super nice. But now we can do even more. I can solve equation 3 prime. From equation 3 prime, I can solve it for VB prime, specifically VB prime squared. VB prime squared is going to equal VA squared minus VA prime squared. So now I can actually substitute that in for VB prime. And when I do that, I get, let's see, let's call this 3 double prime. And now I'm going to say plugging in 3 double prime. When I do this, I get VA squared minus 2VA prime cosine theta A prime plus VA prime squared. and I made that A not so obvious an A. That looks a little better. And now in place of VB prime, I'm going, or VB prime squared, I'm going to put that 3 double prime. That's going to be VA squared minus VA prime squared. I think you can see that the VA squared being on each side cancels out. And this actually allows us to have VA prime both on the left-hand side as VA prime squared. Or more specifically, since we've now gotten rid of VA squared, there is a term of VA in each of the terms that are remaining, so I can now divide both sides by VA prime. So I divide both sides by VA prime. And from this, I get something really, really nice, and that is going to be, let's see how I want to write this. I think I will do I'll pull the VA primes, which was squared on the right hand side, the negative one. If I pull it to the left hand side, it'll become positive, and then I'll get 2 VA primes squared. So I'll do that. 2 VA prime squared. That takes care of this term and this term. And now I'm going to push the 2 VA, which was 2 VA, VA prime cosine theta A prime. I'm going to push that to the right hand side, but we now only have the VA with no VA prime. So this, man, there it goes again. Let me make this a little cleaner too. So now pulling it to the other side, I get 2 VA prime, and this is actually supposed to be VA prime squared, right? Oh, yeah, this will be before I divided by VA prime. So that's why you're seeing that VA prime squared. Now I get 2 VA, VA prime, cosine theta A prime, like that. But now you can get rid of the actual extra VA prime, and that gives you that 2 VA. Yes. That gives you 2 VA prime is equal to 2 VA cosine theta A prime. You can see now that the actual 2's cancel out as well, and VA prime is just equal to VA cosine theta A prime. So if we assume A is the one that went at the positive angle, then we can go ahead and conclude that VA prime, which equals VA cosine theta A prime, is equal to, now I'm going to plug in the figure, which is 8.2 times 10 to the fifth meters per second times cosine of 60 degrees. And that gives me 8.2 times 10 to the fifth times cosine 60 equals 4.1 times 10 to the fifth. So that's one of the answers. Now all I have to do is use my other expression, which I'd already solved for VB prime. Remember, we found that VB prime is equal to VB prime squared is equal to VA squared minus VA prime squared. So we should be able to find that VB prime is equal to the square root of VA squared minus VA prime squared, like that. Therefore, VB prime is equal to the square root of 8.2 times 10 to the fifth meters per second quantity squared minus now the other one, which is 4.10, the zero being an extra digit that's not a sig fig, squared like this. And that is going to give me 8.2 times 10 to the fifth squared minus 4.1 times 10 to the fifth squared. That gives me 5.043 times 10 to the 11th. Okay, meters squared per second squared. And now I'm going to take the square root of that. And that gives me 7.1 times 10 to the fifth. Meters per second. So that's another answer. But now we need theta b prime as well. And what we can do for that one is we can take any of the equations really, but probably equation, what did I call it before? Equation 2 prime would be the best. So that equation was 0 is equal to VA prime sine theta A prime plus VB prime sine theta B prime. That means sine theta B prime is equal to negative VA prime sine theta A prime divided by VB prime. So sine theta B prime is equal to negative. Now VA prime we just found was 4.10 times 10 to the fifth meters per second, and sine of theta A prime was sine of 60 degrees. And then we're going to divide that by VB prime, which was 7.10 times 10 to the fifth meters per second. So if I take 4.1 times 10 to the fifth and divide it by 7.1 times 10 to the fifth, which obviously didn't even need the 10 to the fifth there, I get 0.577. Now I'm going to multiply that by the sine of 60, and that gives me 0.5, and of course it's negative 0.5000. Now that's way more digits than we need. And of course, we also know that when the sine is equal to 1/2, then the angle is 30 degrees. So that tells us theta B prime is actually equal to negative 30 degrees, which is what I suggested. And that's because, again, if the collision is elastic and with two masses that have or two identical masses, then elastic collision forces it to obey the Pythagorean theorem, and the Pythagorean theorem is only true if VA prime and VB prime are separated by 90 degrees, and we already had VA or theta A prime or theta B prime, whichever one we chose it to be, was going to be a positive 60 degrees. Therefore, the other one had to be a negative 30 degrees to make it 90. So, anybody have any questions with that? Okay. Your book has a nice section on page 244. It says problem solving, momentum conservation, and collisions. I highly recommend you read that over, but at the end of the day, you really need to understand this process that I did where I took the momentum in the x direction, I pulled all the VA terms to the left, and then I squared both sides of that equation. Then I took the momentum in the y direction, put all the VAs on one side, the VBs on the other side, and squared both sides just like I did the x equation. And then, of course, I had the conservation of kinetic energy that was allowed for me to plug in. But before I did that, I actually added the last terms of the conservation of momentum in the x direction and the conservation of momentum in the y direction, that allowed me to get rid of the sine squareds and cosine squareds because sine squared plus cosine squared is equal to 1. So that's the big trick. Anybody have any questions on that? All right, so we've got a little bit of other stuff left to cover within this chapter, and it's really just what we call the center of mass. So it turns out, I'll just give you the formula for the center of mass, specifically in terms of a discrete number of objects, and then I'll give you the integral version as well, and I'm going to show you the discrete formula is really pretty straightforward chucker solution where you're just taking the coordinate of each piece that's part of the system and you're multiplying the x times its mass, the x of the coordinate for that object times its mass plus the x for the other object times its mass plus the x for the other object times its mass, and then you're dividing all of that. Once you've done all the masses, you're dividing it by the total mass, and that gives you the x center of mass. Then you do the same thing with the y coordinate of the center of each of the objects, and so on and so forth. So what those formulas are is x center of mass is equal to m1, well, actually, I'll write m1 x1 plus m2 x2 plus dot 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 m n xn, meaning I'm assuming there's n particles, capital M, and m1 plus m2 plus dot 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 plus mn. That is the x center of mass, and there's a similar formula for the y center of mass, and that is m1 y1 plus m2 y2 plus dot 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 plus mn yn divided by m1 plus m2 plus dot 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 plus mn. So those are our formulas for any collection of n items. So if you're imagining, for instance, imagine you're a waitress and a waitress or waiter, and you want to hold a tray up. Okay. Now you take this tray that you're carrying out. You've probably seen people do this before, and you put the individual items. Maybe there are a bunch of glasses of Pepsi tea or whatever, and you put them at various spots. Well, each of those has a mass and each of those has a location on the spot. So in principle, you could sort of draw a coordinate system on the tray. Maybe the center of the circular tray would be the origin. Maybe straight to the right would be the positive x-axis, and straight forward would be the positive y-axis. And then if you wanted to be able to figure out exactly where you're supposed to put your hand after you put all those things on the tray, then the answer to that question is at the center of mass of that system. Now, if the mass of the tray itself is really, really small, you might be able to get away without even taking that into consideration. And that's quite often the case, but you might not. Okay, so you got to be careful. But what you do is take the first glass, take its x and y coordinates, and you want to find the x center of mass, which is how far left and right from center that you actually want to put your hand. And what you're going to do is take the first object's mass and the first object's x coordinate, in other words, the x coordinate at the center of the bottom of the glass, and then do it for the second one, and then do it for the third one, and all the ones that are on there. And then once you sum up all those m's times x's, then you're going to divide it by the total mass, and that'll give you the x coordinate of the center of mass. So somewhere along the axis, which we imagined was the x-axis going from the left edge of the circular platter through the center of the circular platter, which is the origin of the coordinate system, onto the right edge of the coordinate or excuse me, the right edge of the platter. Once you have that, you can actually figure out where X center of mass is, and you put your hand right under that. But now you got to figure out how far forward and backwards of that same line you want to be. Well, that's the Y center of mass. So you're going to take the Y coordinate of the first glass and multiply it by the M. Take the Y coordinate of the second mass, multiply it by the M, its M, and keep on doing that until all the masses are accounted for, and then you say M1x or M1y1 plus M2y2 plus M3y3 until you're done. Divide that by the total mass, and that will give you how far, if it's positive, how far forward of that line straight through the center that ran left to right, how far forward you'd put it. But if it turns out to be negative, it's how far backwards from the center you'd put it. And then if you put your hand like this by holding your hand out instead of holding a single pinky, you would give yourself a quite a bit of room for error. But in principle, if you actually wanted to hold it up on your one finger and you were strong enough, then you could literally put that finger right under the XCM, YCM of that tray and be able to hold it up. Now, that's all going on the assumption that the platter uh, wasn't significantly massive compared to the total mass of everything else. If it was, you just say, well, wait a second. There's also another M and X, and it's the mass of the platter. And obviously, the center of mass of the platter in the coordinate system we drew was X equals 0, Y equals 0. So you'd have a zero term on the top for M times X, but you'd have an additional M on the bottom. But either way, that would actually give you the center of mass. So that physically, hopefully, helps you understand what the center of mass is, and you can sort of see why it looks a little bit like a torque formula. Like if you wanted to calculate the torque, let's say, instead of a platter, let's say we were holding this thing up. If I wanted to put, let's say, this object right here, and my coordinate system is this line and this line, I would take this particular x, y coordinate and multiply the x coordinate times m and so on and so forth for each of the things I put up on there. Now, if I wish to balance it, then I have to find the center of mass of the calculator bottle system, and I could then place my finger under it. But with the one object, you can see that the torque from, let's say, from the coordinate origin, let's say the y-axis is right here, the x-axis is right here. This seems to be lying right on the x-axis. But if I measured the distance from the origin to the center of that bottle, that would be its x coordinate. Now, if I took m and multiplied it by that x, that would be the top of the formula for, or one of the terms of the top of the formula for the x center of mass. But if you instead did m times x times g, the mg would represent the weight of this bottle, and that's a force acting straight down and perpendicular to the actual calculator. And the distance x would be a lever arm, which is perpendicular to the mass, and that would exactly be equal to the torque. So mgx would be the torque. By doing that, you actually have figured out that the m1x1, if you combine that with the term in the bottom being m1 times, or just plain m1, if you add a g to both of them, the g's would cancel out. You'd still get the moment. You'd still get the center of mass, but in this case, it'd be the center of weight. And not only that, you'd see that the m1 x1 is just sort of calculating the torque about the axis. So hopefully that is a physical description that helps you make some sense. I know we haven't covered torque yet, but you probably all have some sense of torque. And I can't remember if we even did a lab on torque yet. I don't think, no, we didn't. There's actually a real easy lab on torque. I wish I would have done that before now, and I might later. But anyways, anybody have any questions on that? Now I'm going to skip example 914 because well, no, let's do example 914 because that one's easy enough and I can just show it to you really quickly. So let's do example 914. Yeah, I got time. So example 914 says center of mass of three guys on a raft. Three people of roughly equal mass M on a lightweight air-filled banana boat sit along the x-axis at positions XA equals 1.0 meters, XB equals 5.0 meters, and XC equals 6.0 meters, measured from the left-hand end as shown in figure 924. Find the positions of the center of mass, ignore the boat's mass. Now, in this case, you're talking people, even if they were kids, they'd still be on the order of, 50, 60 kilograms or something like that. And the banana boat, even when it's filled with air, is probably going to weigh on the order of a couple kilograms. So you can imagine a factor of 10 at least bigger are the masses of the people over the mass of the banana boat. So that should be fairly obvious. What I'm going to do is say XA is equal to 1.0 meters. XB is equal to 5.0 meters. And XC is equal to 6.0 meters. MA equals MB equals MC equals M. And now I'm going to draw my coordinate system with the banana boat like this. So here's my X, there's my Y. And yes, you sort of have to make a coordinate system every time. Or I shouldn't say sort of. You have to make a coordinate system every time. It's perfectly acceptable for you to put the origin of the coordinate anywhere you want, and it's perfectly acceptable for you to put the X-axis pointing any direction you want and the Y-axis at 90 degrees from that. In principle, you could do other angles, but you don't want to mess with that. Either way, when you do that, it turns out to be really easy or really hard. But if you have some way of putting all along one line, then it's really smart to choose that line that they're all along as like the x-axis direction. So if I now imagine my banana boat, I'm looking from the side, by the way, not from the top. So here's the banana boat, which looks something like this. Okay, so there's our little banana boat. And what we're saying is right here at the 1 meter mark, and then at the 5 meter mark, and then again at the 6 meter mark, are masses M, M, and M. Okay. So what we'd want to find is where is the center of mass. Now, this isn't that helpful because the banana boat, if you actually tried to hold it up with the people on it, the banana boat is just so weak, it would just crumble over. But if you instead imagine this was maybe a 4x4 or a 6x6. 6x6 would definitely hold it, but a 4x4 would probably hold it as well. But if you actually laid that out as a 4x4, then in some sense, the 4x4 would still be way lighter than the people, but you could literally hold up the 4x4 at the center of mass, and with the people sitting on it, it would be balanced perfectly. Okay, if you wanted to take into account the center of mass of the 4x4, well, the 4x4 is very symmetric object, so its center of mass, for starters, would be right along the center, along the length of it. And then if it was, let's say, 20 feet long, 10 feet from the left end would be dead center. I mean, you just assume that the 4x4 is fairly uniform. There's a high probability that you're not going to have any huge knots made of significantly different material that makes the weight be shifted more to one side than the other. So you'd expect the center of mass to be the actual geometric center, and then you could just balance it under the center of mass. So that's a way you can think of this as instead of it being a banana boat, think of it being a diving board or a 4x4 or a 6x6, and you're trying to hold these people up. So let me go ahead and calculate what the x center of mass is. So the x center of mass is going to be m times 1.0 meters. Now notice the danger here. By putting the meter in, it looks like the m. Uh, to combat that, I'm going to leave the meter off. That'll be what I do. What I could have done is change the mass to capital M, but I already wrote them as small m. So I'll just leave it be for right now. So m times 1.0 plus m times 5.0 plus m times 6.0 divided by all the masses, which would be m plus m plus m. So m times 1 plus m times 5 is 6 times m. 6 times m plus 6 times m would be 12 times m. And then all of that is divided by 3 times m, which gives us 4.0. And notice I didn't write the meters in there, so I shouldn't really write the meter here, but we know that's the unit that's going to come out. But that is how you calculate the center of mass for this object. So the x center of mass would actually be right about here. And I didn't really draw this to scale. As you can see, I used roughly 1.5 squares to represent 1, but I drifted quite a long ways from 1 before I wrote down the 5, and then I came back to the left of the 5, 1.5 squares, to get the 4, but there's really not necessarily reasonable to assume that's where it is, but that's roughly what you get. Anybody have any questions on that? All right. If you wanted to take into account the center of mass of the banana boat, you'd then put mass of the banana boat on the numerator times, let's say, since the banana boat appears to be going 7 meters by symmetry, I'd say 3.5, but that would make it a lot different because the mass of the banana boat is significantly different from the mass of the people. So you'd have to you'd have to figure out exactly what is the mass of the individual people and use that, or at least find a relationship between the mass of one person and the mass of the banana boat, and that would allow you to work it out. Now that we have that, I want to go ahead and show you the continuous formula for the center of mass. So instead of having individual countable discrete objects, you might imagine that we'd have a continuous mess of material, like for instance the individual pieces of plastic that make up a platter or a tray or something like that. Each of them are infinitesimally wide and infinitesimally wide forward and backwards, as well as infinitesimally wide left and right. And of course, the thickness might be something, but if we're just thinking about it being one uniform thickness, you might not even need that third dimension. But when we go to do something like that, then how do you calculate the center of mass? Well, the center of mass in that case, xcm, becomes the integral of x dm divided by the integral of dm. Notice it's like x times m plus x times m plus x times m in the numerator, and the denominator is like just m plus m plus m plus m. So it looks just like the formula we had before for the discrete case, and similarly, the y center of mass would be done the exact same way. Oops, except you got to put a y in there, not an x, like a crackhead. So y dm over the integral of dm. And I'm going to tell you something that will be helpful to you not only this semester, but next semester too, if you take the 242 class. In general, we say dm is equal to lambda times dl. That's, for instance, if you have a long rod and it being a rod, it has a physical dimension, let's say left and right, but forward and backward, it's infinitesimally wide, and up and down, it's infinitesimally wide. That is something that's one dimensional. And you could say the differential mass is equal to some constant called the linear density time lambda times the differential length dl. In other words, if you integrated it, you could also say m is equal to lambda times L, assuming lambda was a constant. If lambda wasn't a constant, all bets are off. But if it's not one dimensional, you could also say it's sigma dA, where dA is a differential area element, maybe dx times dy or something like that. But we're sticking to single integrals, so we got to be a little smarter than that. And then, of course, if you had, oh, and I should say that in that case, m is equal to sigma a if sigma is a constant. But if the object's not two-dimensional and it's in fact three-dimensional, then we'd have rho dv, and of course that tells us that m is equal to rho times v. And again, that's for rho equals a constant, just like sigma was a constant, just like lambda was a constant. But in principle, rho, sigma, and lambda do not have to be constants. So this little part that I wrote with these dm's is critical for you to actually do a calculation. So let's show you a simple example first. Let's imagine, calculate the cm of a broomstick. Now, I say broomstick, but I really just mean a very uniform piece of wood that's, basically a cylinder. Okay. And not only that, I'm assuming the radius is going to be very small compared to the length. So I'm going to put this broomstick on a coordinate system, and the coordinate system will be like this. So this is my x-axis. This is my y-axis, and technically this is going to be a three-dimensional object because it's a broomstick, but I'm going to pretend like the dimension vertical is very, very small, and the dimension in and out of the page is very, very small, but the dimension going left and right is quite significant, like that. And in fact, I'm going to say that length right there is L, and being that it's uniform, the mass is uniformly. Good Lord, I wrote that so small, I know you're not going to see it. So the mass is uniformly distributed. What does that mean? Well, that means in this case, it's acting like a one-dimensional object. And what I'd say is if I cut a centimeter length of the uh, actual broomstick, and I cut out 1 centimeter length of it, and I weighed it, I would get some number. If I took that centimeter and divide it by that mass, I would get the number that sort of looks like lambda. So, for instance, lambda might be 3.5 grams per centimeter, right? Now, if I took and grabbed another piece at random anywhere else from the broomstick, and I removed, we don't even have to restrict ourselves to a 1 centimeter length. We can actually consider a 2 centimeter length. If I took a 2 centimeter length, in that case, I would find that weighs 7.0 grams per 2 centimeters. Okay. Now, in doing that, what I've discovered is that this quantity lambda is really just the mass per unit length, and that's what I meant when I was saying dm is equal to lambda dl. Okay, so any 1 centimeter length or any 12 centimeter length or any half a millimeter length or anything like that is always going to have the same mass per unit length. Therefore, I can say that a differential mass of a small segment is equal to that linear density lambda times the length. So that's why I'm saying dm equals lambda dx. So let's look right here and say this quantity is dm, and since the length of it is parallel to the x-axis, rather than call it dl, I'm just going to call it dx because obviously I'm measuring in the x direction and I'm going to use the x variable. So this dm is going to be lambda times dx, where that lambda is the 3.5 grams per centimeter. Of course, you'd normally use it in kilograms per meter, but whatever you use, if you're just consistent with your units, it should work out. Now, additionally, I'm also going to say that the position of that particular mass element is over a distance x because obviously it's measured along the x-axis. Now, can anybody tell me what X value you think the center of mass is going to be for this broomstick that's uniformly distributed? It's very important for you to make a guess at this, even if it's a wrong guess, because you can then check your work. And if it doesn't match, you know you either made a mistake on the work or you obviously made or didn't understand the situation to begin with. So, does anybody have an idea what the center of mass, where the center of mass of a broomstick would be? Now, again, it doesn't have a broom on the end, so this is just the stick. Would you grab it like if the broomstick was, let's say, 4 feet long? Would you grab it 1 foot from the end and expect it to be able to hold up like on your fingertip? What about 3 feet from the end? What about 2.5 feet? There you go. Thanks you. Thank you. Eli. Excuse me. Yeah, it'd be this geometric center. So we expect this answer to come out to be L over 2. Okay. I just use the symbol L, and that allows for any length. And lambda is a constant that allows for any length as well. I'm going to say the total mass is equal to M. And of course, that means L is equal to, or excuse me, that means M is equal to lambda times L. So we know that lambda will in fact be M over L. And that's pretty much what it is normally, except sometimes it could be a functional value. So now let's go ahead and calculate it. The x center of mass, it equal the integral of x dm over the integral of dm. The integral of x dm is going to be the integral of x from x equals 0 to L of dm, and dm is lambda dx. And then, of course, we don't have to work the bottom at the same time. So I'm going to write it down there and I'm going to work out the top and then I'm going to work out the bottom. But the bottom is going to be just the integral of lambda dx from 0 to L. So this becomes lambda times the integral of x dx from 0 to L. And of course, the integral of x dx is 1/2 x squared. So this is going to be 1/2 lambda x squared evaluated from 0 to L. And of course, that's going to be 1/2 lambda L squared. Now I'm going to do the denominator. And what we're going to get is the lambda comes out in front, and it's going to be the integral from 0 to L of dx. And of course, the integral of dx is just x. So this becomes lambda times x from x equals 0 to x equals L. And of course, that's obviously lambda L. Now you can see that this L squared is going to cancel out, leaving L to the 1 power in the top. This lambda is going to disappear as well. And lo and behold, we got exactly what we expected, L over 2. So that's how you calculate a center of mass for a simple object. Now, a more advanced one and one that's really relevant, especially if you're taking statics right now, because distributed loads and stuff like that often have a triangular form. So it's really helpful to be able to find the center of mass of a triangle. And I'll tell you the rule. The rule is the center of mass of a triangle is always 2/3 of the way from the narrow end to the thick end. And that might not seem obvious right now, but let me explain to you by doing a calculation. So let's do another center of mass calculation. This time, here's my coordinate system. This is X, this is Y, and I'm going to draw my triangular plate. So this would be what your calculus teacher would call a homogeneous lamina. Okay, homogeneous means it's uniformly distributed mass. Lamina means it's a two-dimensional object, even though two-dimensional objects don't exist. Okay, so in other words, it has a thickness in the z direction, but that thickness is so small compared to the width and the height that we're just going to ignore it. And what I'm going to say is that this dimension is w, and I'm going to say that this dimension is h, and I'm going to say its total mass is equal to capital M. So I'm pretending like I know M, H, and W. And it is uniformly distributed. That's the homogeneous part I was telling you about. So uniformly distributed mass. And uniformly distributed mass means, in this case, it's two dimensions. So that means dm is equal to sigma dA, where sigma is equal to a constant. Now, I told you already that lambda was the mass per unit length, and you can probably see from when I talked about sigma that sigma is the mass per unit area, and you can probably also see that rho is mass per unit volume. So when it's uniformly distributed, that means either the lambda, if it's one dimensional, the sigma, if it's two dimensional, or the rho, if it's three dimensional, is going to be a constant. So anybody want to take a guess at what sigma would be for this? Okay, well, we're running out of time, so I won't wait too terribly long. But in this case, sigma is equal to mass per unit area. So in this case, I'm going to say sigma is equal to m, which we call the total mass, and the area of a triangle is 1/2 h times w. So you could, in fact, call it 2m over hw. Not that we necessarily need it, but it's good for you to understand what the sigma is, what the rho is, and what the lambda is. So I'm going to calculate the center of mass. So x center of mass. Remember, I told you it's 2/3 of the way from the thin end to the thick end. So if we go from the origin to the right along the x-axis, we see the thin end is at the origin and the thick end, notice it's vertically very tall, at the W end. So if I go 2/3 of the way towards the W end, then the x center of mass should be 2/3 W. So that's what we're expecting. Similarly, if I wanted to calculate the y center of mass, I expect it to be 2/3 of the way from the thin end to the thick end. So in this case, we're going to start up at y equal h, and you see that that is the thin end. It's a pinpoint wide, but when you get to y equals 0, the width is w. That total height is h, and 2/3 of the way from h towards 0 is 1/3 h. So we're going to say the y center of mass should be 1/3 h. Now let's calculate it. X center of mass equals the integral of x dm over the integral dm. The integral of x dm, just working that first part, I am going to take and choose a differential area element. So here's my little Riemann rectangle, if you will. The width of this guy is dx. Obviously, it'd be like a dl or something, but it's parallel to the x-axis, so it's a differential change in x. Therefore, its width is a differential change in x dx. Okay? Now, the height of this rectangle is, of course, the y value for this line. Okay, now you can probably remember y equals mx plus b. Let me write this in red. Y equals mx plus b, where m is the slope, which is rise over run. Clearly, the slope of this line is h over w, and the intercept is where along the y-axis the line hits the y-axis. In this case, it hits the y-axis at 0, so y should be equal to h over m times x. So I'm going to integrate, since we're integrating along the x direction, I know I'm going to have to integrate from x equals 0 to w. The x is going to stay there. This little rectangle right here is my differential mass element, and that is given by sigma times the differential area. I'll just call it sigma. We know it's supposed to be 2m over h times w, but dA is the area of that rectangle. Well, the area of that rectangle is the height, which is h over m times x, times the width, which is dx. So I'm going to have sigma, actually, let me go back to blue now. I'm going to have sigma times h over m times x times dx. Again, I'm working one at a time, so I'm going to stick with the numerator right now. We can now pull out the sigma, the h, and the m out in front, and that's going to give us the integral of x squared dx from 0 to w. And of course, the integral of x squared is 1/3 x cubed. So we're going to get 1/3 sigma h over m, and x cubed is going to be evaluated from 0 to w, so that's just going to become w cubed. Now the bottom is exactly the same except it's lacking that x, so this is going to be the integral from 0 to w of sigma h over mx dx, and that's going to be sigma h over m pulled out in front times the integral of x dx, again from 0 to w, and of course the integral of x is 1/2 x squared, so this is going to be 1/2 sigma h over m times x squared, but x squared is going to be evaluated at w and 0, so that's just going to be w squared. Now I can work all this out. I get 1/3 divided by 1/2 is 2/3. The sigma h is going to cancel out with the sigma h. The m is going to cancel out with the m, and I'm going to get w squared over w, or excuse me, w cubed over w. So this is 2/3 w, which is exactly what I predicted. Now, I've got a ton of videos like this on my YouTube channel, but time is up, so I should go ahead and let you guys go. Actually, is time up? Is it supposed to be running 7:50 or to 7:30? I think it's supposed to run to 7:30. It's only been a whole semester. I don't know why I wouldn't know that right now. Let me double check. Oh, actually, I completely made this time up, so I guess it's whatever the heck I made it. But anyways, I do think it's 7:50, so that might be a little bit better. I'm just checking the time that a normal class meets just in case I've forgotten. Uh, you know, late night, sometimes you forget a little bit. So 5:30 to 7:50. Oh yeah, it does go for 7:50. So I got a few more minutes. Cool. Whew, I think I literally had recorded that as 7:30. All right, now that we have that, let's try to calculate the y center of mass. This one's going to be a little bit more complicated, but it's good that I have enough time because I want to show it to you. Does anybody have any questions on this before we move along? Because if you don't understand this, it could be a lot nastier on the next one. Okay. Looks like no questions, so let's move along. I'm going to draw the object again because it's really important that I have a clean diagram so you can make some sense of what I'm talking about. So here's my x-axis again. Here's my y-axis again. Now, what you might not have noticed is when I'm going to calculate the center of mass for the x coordinate, I have the integral of x dm. So x is the integrand. When you choose a differential mass element, dm, like I did, that's that little rectangle, it's important that the x value in the quantity dm is not significantly different from one part of it to another. So, in other words, the left hand edge of the differential mass element is at a distance x, the right hand edge is at a distance x plus dx. And if I had a macroscopic measure of that width, it would be x to x plus, 4x or something weird like that. That wouldn't be acceptable because I'd have to go back and then calculate some average value of x that faithfully represents the dm. So it's very important that you keep the differential mass element very, very thin along the coordinate you're integrating or along the integrand. So it's very important you do that. That's why I'm going to do a lot more weird stuff that you might not have thought of when I go to calculate the y center of mass here. So I'm going to draw the diagram again. Okay, I could draw that a little better. I'm going to use my auto draw. That's a lot better. And now I'm going to do it right here as well. But again, this quantity is a distance w away, and this quantity is a distance h away. And again, this is the homogeneous lamina, but I need to calculate the y center of mass. And the y center of mass is the integral of y dm over the integral of dm. So I need the y to not change very much from any part of the dm to any other part of the dm. So if I were to choose the exact same center of mass, or excuse me, the exact same dm I had last time, you'd see the y changes a lot. It changes from, this top value up here to this low value down here. That is too big. I really need something infinitesimally wide in the vertical direction. So if I drew a box like this, that would be acceptable. So that's what I'm going to do. I'm going to take my differential mass element to be this quantity. Okay. And what I'm saying is the height of this object is a height dy. And of course, that means the distance from here, from the x-axis up to the bottom of that dx is a height y. And the y varies no more than y to y plus dy. So that means this differential mass element is acceptable. So this is dm, and it's going to equal sigma times dA. Now we can see the height is dy, so that part's easy enough. But what I've got to figure out is what is the width. Okay, well, I know the x value here is w, and I know the x value here is given by x equals a function of y. Remember before we used y equals a function of x as linear. Now I can say x as a function of y and figure out that way if I wanted. So this equation, which we know the equation for this, we know this equation of this line is y equals h over m times x, and that means x is equal to m over h times y. In other words, if you're asking for a particular x value for a given y, I can just plug in that y, multiply it times m, divide it by h, and that'll give me the x. So that is a way that I can actually find the height of this rectangle. The height of this rectangle is, in fact, this is the value x, and this is the value of the height of the rectangle. So the height of the rectangle can be thought of as w minus x. Okay? So now I'm going to continue. and say the integral from y equals 0 to h of y. Now my dm is going to be sigma times, now I'm going to do my w minus x. So this is w minus x, and then times dy, because the w minus x is the width of that rectangle and the dy is the height of that rectangle. Now I need x in terms of y. In other words, I don't want an x in there, and I have an expression for x in terms of y. I just did it by solving for x in the expression y equals h over m times x. So now this integral is going to become the integral from y equals 0 to h of sigma y w minus m over h times y times dy. Now, I've really left, actually, I didn't leave myself enough room, so I'm just going to say this is the top. Okay, so I'll work out the top and then I'll work out the bottom in a second. So now I can see that the sigma definitely comes out in front, and I'll say the integral from 0 to h of wy minus m over h y squared dy is equal to sigma. There it goes, changing the pen again. Sigma. Now the integral of wy is 1 half wy squared. Evaluate from 0 to h is 1 half wh squared. So I'm going to say 1 half wh squared for that first integral. Now the integral of negative m over h y squared is 1/3 m over h y cubed. That becomes 1/3 m over h, and of course evaluating it at h and 0 gives me h cubed. So that's the actual value we have. Now I'm going to simplify and say this is sigma. There's obviously, ooh, that's supposed to be a w over h, not a m over h. I don't know why I wrote m, but make sure y'all correct this. Remember that came from the original equation, and you see, I wrote it wrong there too. Good Lord, Jiminy. But I wrote it right in the integral. Or did I? Oh, no, it just canceled out. So, yeah, that was all wrong to begin with. I think I just saw the M for slope and kept putting it in there. So make sure you guys correct this. I think y'all all probably, if you were paying attention, I think you would have realized that that was supposed to be W. Uh, and maybe you saw it and just ignored me. I don't know, or maybe I just blew you away and you didn't understand that. That's okay too. I would have asked you to that. I'd prefer you to go ahead and find out what that is. But that is supposed to be h over w. Remember the way I did it was y equals mx plus b, and m is rise over run. Well, the rise was h and the run was w, so there was no reason for it to ever be m. I don't know why it became that. Let's do this. So again, I don't know why I changed it to M like a dummy, but anyways, I've now corrected it. Hopefully that's good enough. And yeah, now I got to fix it in here too. So this one's going to be, whoa, did it? W. And this one's going to be W. And this one's also going to be W. Man, I went a long time with that and didn't even realize it. Okay, now we're in a spot where we can make use of this stuff. The sigma is going to be in there. Uh, the W is going to be in there. In fact, what I now have is sigma 1 half minus 1/3, because notice the WH squared is what you get when you cancel out the exponent of 3, replacing it with a 2, and canceling out the h in the bottom. That gives you WH squared. So I can just put this as 1/2 minus 1/3 WH squared. Okay. Now, 1/2 minus 1/3, the least common denominator is 6, so that'd be 3/6 minus 2/6 would be 1/6. So the answer is 1/6 sigma times WH squared. Now I've got to do the bottom, which is going to be a lot easier as you'll see, but let's do that. Remember the formula, the answer formula is an integral over an integral. So I'm now doing the bottom integral. The integral of dm is going to be the same dm I used before, which was sigma dA. And you see that this sigma dA became w minus w over h times y. So this is going to be sigma integral w minus w over h y dy. So when I integrate this, I get sigma times the integral of w with respect to y, and of course this is integral from 0 to h again, but the integral of w with respect to y is wy, and then I evaluate that from 0 to h, so I just get wh. And then the integral of w over h times y is 1/2 w over h times y squared. So 1/2 w over h times y squared. But y is going to be evaluated at h and 0, so that's going to become h squared, like this. So you can see I'm going to have a common factor of WH again, because this H in the bottom is going to cancel out, leaving a 1 in the top there. So this quantity will become, now I have sigma WH times 1 minus 1/2, which is obviously 1/2 sigma WH. So the YCM is supposed to be 1/6 sigma WH squared over 1/2 sigma WH. And of course, 1/6 divided by 1/2 is 1/3. So we finally get, and I should probably be writing this in a different color since it doesn't fit so easily. I get YCM. Let's just write that a little neater so it separates from this other fraction a little bit. So YCM is equal to 1/6 sigma H, or excuse me, sigma WH squared divided by 1/2 sigma WH. You can see the W cancels out with the W. The H squared cancels out one of the H's down here. The sigma cancels out with the sigma. And then, like I said, 1/6 divided by 1/2 is in fact YCM equals 1/3 H, which is exactly the answer that we predicted. So other than me mistakenly writing M everywhere instead of W, this was all done without much of a hitch. Anybody have any questions on this? Now, to date, this is among the hardest or maybe second hardest type problem that you're going to be required to do in the whole 241 course. The original one being how we integrated some a as a function of time, and given some initial conditions, we were able to find out v as a function of time and x as a function of time, and then we could calculate things like average velocity or average speed. Those can sometimes be every bit, if not more, complicated than this, but this is pretty hard. It does take multiple integrals, and a lot of students just get scared from doing that. But this is also material that you probably, at least I know I did when I took calculus, probably learned it in calculus already, or are learning it right now in calculus or very soon. So, anybody have any questions about this? All right, well, that's it, guys. We have completely finished chapter 9. Remember, your homework, I believe, is due for chapter 18, or excuse me, chapter 8 and 9 are both due the 14th. So you've got like 4 days. Uh, I think that's plenty of time because eight's been up there and we've been finished with eight for a long time. So I had pushed eight back. So the fact that eight was not due until the 14th, if you didn't do it, that's sort of on you. Whereas this one's just one homework assignment from chapter nine and it's due on the 4 days from now. That being said, being 1 or 2 days late is not that big a deal from a homework grade standpoint. So don't worry about that, but definitely get it done. Try to do as much as you want, as much as you can. If you're finding that you're worried more about doing well in the test, the homework is very critical and helps you learn. But if you just need rote, well, if I don't want to say rote, but if you just need a lot of experience, it's probably better to focus on the chapter practice and the practice tests. And later on in the semester, you'll learn that there's a way I can help you guys if your homework grade turns out bad. So just keep that in mind. Darius, I am going to take care of that for you. I'll send an email tonight or tomorrow. I would appreciate if you send me an email tomorrow just to ask me if I did it in case something happens I might forget. But other than that, you guys are free to go. Chat me your first and last name. Don't forget to write async if you're in another class. But you guys are free to go. Thanks for coming. I really appreciate it. Okay, thank you. I appreciate that, Hope. Thank you, everybody. I'll try to post this up tonight. Should be up tonight. If not, it'll be first thing tomorrow. But y'all have a good night. Thanks again. Yes, Adrian.
I'm probably gonna need an appointment set up.
Okay.
God, because I, I'm, s- I'm still, I haven't even progressed at all. Like the past 2 weeks. Because
Uh, well, like I said, I mean, you're doing better than I had worried about based on your last two test grades. So that's pretty good. But yeah, it's certainly.
I have not done. I've barely done chapter 6. I have a serious problem. I have a serious question with chapter 5. It's about the incline problem for chapter 5 when
Mm-hmm.
you include friction.
Right.
It's the difference between the force of friction, regardless of depending on the direction of the force, and the force parallel. And the force parallel. Wait, what am I
You
trying to
mean
say?
perpendicular or normal force?
Mm, no, the gravity parallel. The
Oh, okay,
parallel of
gotcha.
gravity as produced by mg sine theta,
Right.
which I believe is something you have to account
Yeah,
for
that's
all.
the component of weight that's parallel to the incline. If the incline is an angle theta above horizontal, it's mg sine theta, and then the normal force, if no other forces are acting perpendicular to the surface, the normal force would be mg cosine theta.
The force of friction on the incline in the aforementioned mg sine theta, the gravity
Hmm.
always parallel to each other.
Parallel slash anti-parallel. So I mean, mg sine theta is always going to point down the incline.
If it's up, if it's okay, if it's okay,
And
if it's
if the object's sliding down the incline, then the friction's up. But if the object's sliding up the incline, then the friction's down.
if the object is being moved up, it's parallel.
Hmm.
If it's the other way around, it's anti-parallel.
Exactly. Well, friction always is a force that resists the relative motion. So if the object's moving up the incline, friction is going to point down the incline. If the object's moving down the incline, friction is going to move point up the incline.
But yeah, but it's always on basically the same line as the
Exactly. Yeah, it's always got
gravity.
to be parallel. It's just parallel to the surface that it's sitting on.
Direction will be different.
Yeah.